Hello, we're Team 7, Harold and Friends. As part of the Spring 2019 Robotics Science and Systems class at MIT, we chose our final challenge to be 3D mapping and autonomous parking. In order for a robot to be fully autonomous, it needs to have an understanding of its environment, such as a map. So for this challenge, our goal is to have our car Harold create a 3D map of a parking environment as it drives in it. This map will be a 2D occupancy grid alongside a 3D point cloud that identifies features of the environment, such as different colored parking lines and signs. Afterwards, the car will use this labeled 3D map to identify the location of a target parking spot and autonomously park there from a random start point. So how do we create the map? We drive the car in the environment and use LiDAR point cloud data from our Velodyne and images from our Z camera to generate the map. We first use Google Cartographer to create a 2D occupancy grid of the environment and produce a global fixed frame for the map. Since the Velodyne produces more points than we need per second, we downsample our point cloud to speed up the mapping process. We decided to use a voxel grid filter, which groups points into 3D boxes and computes the centroid of the points in each box. We could then semantically label these downsampled point clouds by using the image data from the Z camera. Since all the objects in our space were solid colors, we performed color segmentation to identify the pixels in the image that had a certain color and then drew contours around them. We then mapped each point in the point cloud to a pixel in the image, using a transform between the pixel coordinate and the real coordinate in the point cloud. We do this by projecting points from the frame of the 3D point cloud to the image plane, and then identify the points that fall within our colored contours. These labeled point clouds are then stitched together to create a cohesive map using the Ross laser assembler service, which places all the point clouds in the frame of our overall map. So now that we have a map, how do we park? We had to park between the red lines in the space. So we identify the red points in our point cloud and group them together to draw a line segment representing the parking lines. We then create a goal point in between these lines. We then create an intermediate waypoint between the car's initial location and the goal state. Using the A-star path planning algorithm, we plan a path between these waypoints. Finally, the car uses a pure pursuit controller to follow this planned trajectory and park in between the red lines. We had three main difficulties in our implementation. First, during the semantic labeling, it was difficult to get the frames to align. This was because our Velodyne was shifted from the base frame of the car, and our camera was upside down. This was solved by tuning the frame transformations during multiple test runs. Second, while running Cartographer, our 2D map would shift when we drove fast, which caused inconsistencies in coloring. The effects of this were mitigated by tuning the Cartographer parameters. Third, our Z camera was not as fast as our LiDAR, so we had to stop while mapping to make sure both data sources were seeing the same thing. We want to thank our wonderful TAs Michelle Tan and Sabina Chen for helping us tackle these difficulties and ultimately complete the final challenge successfully. Also, a big thank you to the rest of the technical and communication staff for their support. We hope that you enjoyed this video and learned something new. Thanks for watching and good luck with robotics.